Welcome to This Explainer. Today, we're going to decode the exact architecture you need to design a URL shortener. You know, something just like bit.ly. If you've ever found yourself wondering how the internet shrinks those massive, clunky web addresses into tiny, shareable links, or if you're gearing up to tackle a high-stakes system design interview, well, you're in exactly the right place. We are going to build this entire system from the ground up, step by step, using this precise architectural blueprint. Let's get into it.
So here's the game plan for tackling this problem. We'll start by defining the URL shortener, then we'll do the math, figure out how to actually generate the shortcode, scale our unique IDs, and finally, we'll map out the whole high-level design.
Starting off with Section 1, defining the URL shortener and really clarifying our scope.
Put yourself in the interview hot seat for a second. Before drawing a single box on a whiteboard, you have to ask these scope questions out loud. Like, do these links live forever, or do they expire? Are users picking their own custom shortcodes? And, hey, do we need to track how many times a link is actually clicked? For today's explainer, we're going to assume standard URL shortening with optional expiry. No custom aliases for now, and we'll treat click analytics as a nice stretch goal.
Now, here's where it gets really interesting. Deliberately choosing a 302 redirect over a 301 is a massive signal of your technical experience. See, a lot of people just default to a 301 permanent redirect. But a 301 gets cached by the browser. So if a user clicks it a second time, their browser just bypasses you and goes directly to the destination without ever pinging your server. That completely kills your ability to track click analytics. By explicitly choosing the 302 temporary redirect instead, you literally force the browser to ping your server every single time, which is absolutely crucial if you want to track those analytics.
Moving right along to Section 2, doing the math. Time for some back-of-the-envelope calculations. Okay, the most crucial takeaway here is this absolutely staggering 100-to-1 read-to-write ratio. Just think about how a URL shortener is used in the wild. A link gets generated exactly once, so one write, but it might get clicked on Twitter or YouTube thousands and thousands of times. Those are our reads. This incredibly lopsided 100-to-1 ratio basically dictates our entire architectural strategy moving forward. It means we must hash aggressively, and we absolutely cannot over-engineer our write path. Let's break this down. If we assume 100 million new URLs are created every single month, that actually comes out to a surprisingly low average of just 40 writes per second. But because of that wild ratio we just talked about, our reads are going to hit anywhere between 10,000 and 20,000 requests per second at peak traffic. Crazy, right? And as for storage, well, assuming a 500-byte record size for the original long URL plus some basic metadata, if we retain 5 years of data across roughly 6 billion records, we're looking at needing about 3 terabytes of storage capacity.
All right, Section 3, generating the short code. This is the core design decision.
This perfectly illustrates the two main paths we could take here. Option A is taking the long URL and hashing it with something like MD5, and then truncating it. The problem with that? The birthday paradox. Random hashes will inevitably collide at scale. You'd have to constantly check the database to see if the hash exists, append a salt, hash it again, check again. It's a mess. It creates these nasty retry loops on your write path that just slow everything down. Option B, on the other hand, is base62 encoding and auto-incrementing ID. Because the underlying numeric ID is unique by definition, you guarantee 0 collisions right out of the gate, entirely avoiding those dreaded retry loops. So, why base62? Well, base62 uses 26 lowercase letters, 26 uppercase letters, and 10 numbers. If we restrict our short link to just 7 base62 characters, you're generating 62 to the power of 7 possible combinations. That equals roughly 3.5 trillion possible unique codes. Remember that math we did a minute ago? We only need a few billion for 5 years of data. So yeah, 3.5 trillion is vastly more than we will ever need. That brings us to Section 4, scaling unique IDs through distributed generation. When you're evaluating these options, you'll see a single database auto-increment counter is just way too much of a bottleneck. Now, Snowflake-style IDs, which use timestamps and machine IDs, they're fully decentralized, sure, but they require complex clock synchronization. Honestly, that's total overkill unless you're dealing with massive Twitter-scale traffic. So the absolute sweet spot for our requirement of 40 writes per second is the middle option, range-based allocation. Basically, a coordinator hands out blocks of 1 million IDs to each server. The server then just increments locally in its own memory. It is blazingly fast. And hey, if a server crashes, sure, we lose the unused IDs in that specific block. But with 3.5 trillion possible codes to play with, we really don't care.
Finally, Section 5, the high-level design. Let's map out the whole system.
Let's start by looking at the right path. It flows so elegantly. A user submits a long URL. Our application server grabs a numeric ID from its local block-allocated memory. It then mathematically encodes that number into a 7-character base 62 string. After that, it simply writes that brand new short code and the original long URL mapping straight to our database. And finally, it returns the shiny new short URL back to the user. Boom! No retry loops, no bottlenecking, just a clean write. Now, for the read path, which remember is where the real heavy lifting happens thanks to our read-heavy workload. When a user clicks a short link, the server immediately checks a Redis cache. On a cache hit, we redirect them instantly. But if it's a miss, we read from the database, populate the cache for next time, and then redirect. To really optimize this, we're going to use an LRU, or least recently used, eviction policy on the cache. This makes sure we only hold the hottest 20% of URLs in memory, letting cold, rarely clicked links just naturally fall out. It keeps our redirect latency extremely low without us having to pay for infinite cache memory.
When it comes to storing that 3 terabytes of data, picking the right database category is a massive signal of your engineering experience. Listen, we do not need a relational database here. There are no complex joins, no tricky transactions. We literally just need to look up a key to find a value. So selecting a horizontally scalable key-value store, something like DynamoDB or Cassandra, and then sharding the data, which means splitting it into smaller, faster pieces by the shortcode, well, that perfectly fits our access patterns and scales seamlessly as our data grows over time.
Wrapping up the design, you definitely want to impress your interviewer by quickly rattling off how you'd handle some edge cases. For link expiration, just use the built-in TTL or time-to-live feature of your key-value store. Simple. If users decide they want custom aliases down the line, mention that this bypasses our base 62 math, meaning we just have to introduce uniqueness checks against the database before inserting. And for security, you could easily add a quick step to check incoming long URLs against a known malware or phishing block list before allowing the system to shorten them.
And there you have it, a complete, highly scalable URL shortener. We totally conquered short links today, mastering everything from ID generation and encoding to aggressive caching. But as we look ahead to the next stage of our system design journey, I want to leave you with this provocative thought. What happens to your architecture when the payload you're storing isn't just a tiny URL, but gets massively larger? I'm talking about blocks of raw code or heavy text on a site like Pastebin. How does separating metadata from content change everything we just built today? Keep thinking structurally, keep relying on the math, and I will see you in the next explainer.